So welcome back, everyone. Today we'll be discussing the first quantum algorithm, that is the Deutsch-Jozsa algorithm. In particular, we will start by considering and introducing the concept of constant and balanced function. We'll discuss then the first version of this algorithm, the Deutsch algorithm, and in particular we'll introduce a very important concept, that is the phase kickback. Finally, we'll discuss the generalization that was made by Jozsa for a multiple qubit circuit. Now, the problem that this algorithm tries to solve is try to understand if an unknown function f is constant or balanced. A function f is called constant if it takes the value of 0 or 1 for all the inputs, while it's called balanced if the function is 0 for half of the inputs and 1 for the other half. If we take a single bit input, then the function, when the function of 0 is equal to the function of 1, the function is constant. While when the function of 0 is different from the function of 1, then it's called the function is balanced. To make a few concrete examples, if we take the function 0 that takes the input 0 and outputs 0, or take the inputs 1 and outputs 1, and is described by this oracle over here, then we can say that this function is constant. Likewise, the function 1 that takes as an input 0 and outputs 1, and takes as an input 1 and outputs 1, is also a constant function, and is described by this oracle that you can see over here. Balanced functions are, for example, the function x that takes as an input 0 and outputs 0, or takes as an input 1 and outputs 1, and is described by this control not operation. Or the function x plus 1 that takes as an input 0 and outputs 1, and takes as an input 1 and outputs 0, essentially reversing the previous outputs, and therefore is given by a C0 and an X gate. These two functions are constant, while these two functions are balanced. Classically, to understand if a function is constant or balanced, we need to evaluate the function 2 times. Quantumly, however, we will see that a single evaluation of the function suffices to solve this problem, given a certain quantum advantage. Now, to do so, we introduce now the Deutsch algorithm that has the following circuit representation. We see that it requires an Hadamard gate for both registry and ancillary qubit that are initialized in the state 0 and in the state 1. Then we will need the oracle that we introduced before, the U of f, and we need to Hadamard back the qubit registry and measure it. Let's see what this circuit does. The first step is uses the quantum parallelism concept that we introduced before. When we Hadamard the state 0, then we obtain the output state plus. When we Hadamard the state 1, we obtain the output state minus. So at the end, we have a tensor product between plus and minus. Now let's see what happens when we apply to this input state the oracle U of f. And this is an important concept for quantum computing that is called phase kickback. In this case, it's important, it's relevant to describe what happens when the input state of the registry is an arbitrary input state x that can take the value 0 or 1. Because the state of the ancillary qubit is a state minus, then the input state spelled out explicitly will be a combination of x0 minus x1. The output state will be then the output state of this oracle evaluation will be then the state registry x, f of x for the first state vector, and 1 plus f of x for the second state vector. And importantly, there's a phase shift of pi between the two of them. What this means is that if the function is 0, then if the function of x outputs 0, then what we will get is essentially the same state that we inputted before, so x and minus. However, if the function of x is 1, then what we will have is a shift, is a phase shift where the first term will become the x1, while the second one will be x0. In other words, we will get back minus the input state. We can summarize this result just by saying that the output state will be -1 to the power of the f of x of the input state. And this is famously called the phase kickback trick. And it's a very crucial part of quantum computing. So with this in mind, we can easily evaluate what happens when we have as an input state the state plus for the registry, and for the ancillary qubit the state minus. In this case, in fact, what we will get by using directly the phase kickback trick is a superposition of -1 to the power f of 0 plus -1 to the power f of 1 times the state 1, all tensored by the ancillary state in the state minus. Once we are here, we then need to do something about this state. And in particular, to extract some information, we need to use interference. To do so, we apply an extra Hadamard to the registry qubit, this gate that we can see over here. Now, what happens in this case is that the state of the registry when it's 0 will become a state plus, and when it's 1, it will become a state minus. We can rewrite this concept. We can rewrite this operation just by using the following formula, and we can see that there are two different coefficients for the two different amplitude for the state qubit registry in the state 0 and qubit registry in the state 1. What changes between these two is crucially this plus and minus sign that we can see over here. Once we have this state, to make sense out of it, we need to measure the qubit registry. So let's see what happens when we do measure with this measurement apparatus the registry qubit. If we just directly look at this formula, we can see that we measure 0 with a probability that is given by the square of this coefficient over here. Now, this probability takes the value of 1 when f of 0 is equal to f of 1, and takes the value of 0 when f of 0 is different from f of 1. Meaning that when the function is constant, which is the first case, we will measure 0 with probability 1. While if the function is balanced, so f of 0 is different from f of 1, we will measure 1 with probability 1. Or in other words, we will not measure 0. Let us now see what happens when, instead of taking as an input a single bit registry, we take an n-bit input with n bits registry. So in this case, we initialize the registry as a superposition, as a tensor product between 0 state. So in this case, this 0 over here has to be meant as the decimal number 0, where all the bits are in the 0 state. Then essentially, we apply the same circuit, just generalized to this more general input registry. So let's see step by step what happens in this case. We start, once again, by the state 0, where all the bits are initialized in the 0 state. We now apply an Hadamard to this input registry. What this means, what this shorthand notation means, is that we apply an Hadamard gate to all of the qubits. So this transformation is called an Hadamard transform. And what will happen is that all the states that are initialized in 0 will become the plus state. So the output of this transformation is just a superposition, is just a tensor product of all plus states. Now, this is a very important state because we can also rewrite it in terms of decimal number. we can see that if we expand this in terms of decimal number, this input state, this output state, is actually a superposition of all possible decimal number with equal probability 2 to the power n. So this is what happens when, for an Hadamard transform, when the input state is the state 0. Let's consider also a general case where the input state is an arbitrary input string, an input string x. What happens after we apply this Hadamard transform is that the output state will be still probing the whole space. So it will still, the output state will still be a combination of all possible output strings, of all possible strings in the Hilbert space. But now, because we start from an input state that is different from 0, there will be a certain phase that is acquired. And in particular, this phase is -1 to the power x times z, where z is a label of all this input, of all this output state. So let us now see the first step of the, let us now revisit the first step of the Dolce-Llosa algorithm. The first step, once again, is an Hadamard transform of this n-qubit input. Once again, the Hadamard transform of this n-qubit input is probing the whole Hilbert space and is essentially creating a superposition of all possible input string x. When we Hadamard transform the ancillary qubit that is initialized once in the state 1, then we will get a minus state. So the output state after this step of the circuit will just be described by this by the coherent superposition of all strings x tensor product minus. We now apply to this input state the oracle U of f. And once again, the phase kickback trick helps us out. In particular, the phase kickback trick means that our output state after this operation will be just given by the input state, but with a certain phase shift. So all the string will acquire a phase shift of -1 to the power f of x. Okay, the next step is quantum interference. And in particular, we need this step, once again, to massage the output state in such a way that we can extract some useful information out of it. We do this by applying an Hadamard gate to the qubit registry. And as we saw, when we apply an Hadamard gate, or rather an Hadamard transform, what we do obtain is an extra phase of x of -1 to the power of x times z. We then measure the qubit registry, and now we have to discuss what happens depending on the measurement outcome. In particular, what we are interested in is the probability of measuring the state 0. And by the state 0 here, we mean the decimal state 0. So when all the qubits are in state 0. Now we see directly from this formula that the probability of reading off the state 0 from the qubit registry is given by the sum of -1 to the power f of x over 2n to the power of 2. Now we can easily see that if the function is balanced, meaning that all the function f of x is outputting 0 for exactly half of the input x, then the probability of measuring this state is exactly 0. So you will never be able to measure this state if f of x is balanced. And this gives rise to a way to detect whether the function of f of x is constant or balanced. Of course, there are some caveats here that one needs to be aware of. In particular, the function f of x needs to be either constant or balanced, and no other possibility can be allowed. So we need some insurance to begin with that this function is either constant or balanced. But if we do have this insurance, if we are sure that the function cannot be anything else, then if we measure all the qubits are zeros, we can with certainty say that f is constant. While if you measure any qubit to be in the one state, then the function will be balanced. Now, classically, to obtain this outcome, we will require 1 plus 2n over 2 call of the function f. Well, quantumly, we just saw that one call of the function f and n measurement of the qubits will suffice to give a certainty that the function is either constant or balanced. And this is the first example of an exponential speedup the quantum computer produces. In the next lectures, we will see more of this quantum advantage.